Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, welcome everybody. It's my pleasure to introduce Oukseh Yang to you. Oukseh's visiting us from Queen Mary University, where he's a professor. He has worked for many years on program semantics, program analysis, program verification, and logics that make it easy to specify and verify programs. He got his PhD from UIUC in 1991, and then he spent 5 years in Korea doing a postdoc. Then he moved to Queen Mary University.
Yes.
And he has been there since then. In May, he is going to move to Oxford University. And he'll be here today and tomorrow. If you're interested in meeting him, let me know.
Okay, thank you very much. Sure. And actually, I got degree in 2001, 1991. Then I got degree like 20 years ago. I was a little bit, perhaps too young for. So, okay, means what I'm going to talk about is turned on. Okay, what I'm going to talk about in the perhaps next 50 minutes or less than 50 minutes is going to be what I have done with Oukseh and Rasmus Petersen. And so I will give some words about, before really starting a talk, I want to give some words about kind of research methodology that I and my friends employed in the past couple of years. So the kind of methodology we had was, we were, in some sense, didn't really focus on technology which applies for really wide class of programs. Instead, we wanted to analyze only some small, restricted but interesting class of program with a zero false alarms. So what we believe was, if we focus on certain class of programs, then push the verification technology up to the limit so that it can actually verify some of the property, not with the zero false alarms, then that will help us to come up with the new ideas. So what I'm going to present now is, in a sense, results of that followed from that methodology. So I will tell you kind of program we are interested in, and also kind of property we discovered for the program, and the technology we developed to exploit these properties. Okay, right. So the long-term goal of my research and kind of the thing that I want to do with my friends is to develop automatic verification tool that can verify certain class of program with zero false alarms. So we are interested in real-world programs from, especially real-world low-level code like operating system, in some part of the operating system Linux. And we started this style of research around 5 years ago, I and my friends in London. And then, although it sounds a little bit odd for me to say we made a progress, we actually made, I think we were quite proud that what kind of thing we have achieved, because 5 years ago, what we did was kind of lists reversal and so on. But now we can, we have enough infrastructure and experience so that we can apply to analyze some more realistic code. So one of the examples which I'm going to talk during the talk is deadline IO scheduler from Linux. So I think we made interesting progress. But still, we are quite far from achieving the real goal, which is developing technology that works for, for instance, Linux. And there are many challenges to deal with those, to overcome all the difficulties. And one of the main challenges is this highly shared data structure. That is what I'm going to talk about today. So, another thing which I want to tell you is, I think I'm a bit nervous today. So especially if I'm nervous, my English gets screwed up. So when you have some questions, feel free to ask me. The purpose of this talk, I'm not giving talk for like a conference, so it's not really about like selling. Well, of course, it's about a little bit of selling my stuff, but also I hope you to understand some of the things that I really enjoyed doing. So if you have any questions, feel free to ask me. Okay, so right. So one of the challenges in developing automatic verification tool is complicated data structures. So this is one example of complicated data structure, which you can find in deadline IO scheduler. So deadline IO scheduler, what it does is, whenever you write, say, okay, I want to write like 1 megabyte of file into the disk, then that request is chopped into very bunch of small requests. And those small requests are first saved into a bunch of queues. And from that queue, some scheduler picks the next request to process, and then that request is moved to the next queue. So the first queue you see on the left-hand side, these are the two queues in deadline IO scheduler. And when request first arrived, it is stored somewhere in this queue. It doesn't look like a queue. It's quite complicated, but it's stored somewhere here. And then when IO scheduler thinks, oh, now it's time to process one request, the request is moved from this Q1 to Q2, and then sometime later, it is really written into the disk. Now, one of the challenge to verify such a program is that, the Q2 looks quite okay. It's a doubly linked list, but Q1 looks a bit similar. It looks like there are some structure, but it is quite complicated structure. So the question is, how can it develop verification technology which can verify data structure like a Q1? So when we look at it, we first thought, well, this is so complicated, but we realized actually Q1 has very nice structure, which is, if you look at some of the field, this is just doubly linked list. And if I see another kind of field, this is just red-black trees. So it is two data structure which is implemented on top of one another. And they do it because that allows them to optimize certain operation, which I'm going to tell you later. So what I call that overlaid data structure is that multiple data structures are implemented on top of one another. And this kind of data structures are found frequently in many of these systems code, especially like when I looked at source code of Linux. It's quite common to use it because these two data structures provide different kind of indexing over the data structure, so some operations can be done in a very optimized way. Right, but for program analysis person's perspective, I want to find a little more property about such a data structure, because if I really try to track all the correlation between tree and linked lists, it becomes very difficult to come up with a scalable verification technology. So we looked at the source code, and we realized actually that although these multiple data structures are implemented on top of one another, they are very weakly correlated. Especially the correlation that matters is these data structures are just talk about exactly same set of heap cells. So what we actually have done is that we developed verification technology which can actually exploit this weak correlation property. So I will show you some operation in deadline IO scheduler, and then tell you that the correlation property that I just told you, tree and list are talking about the same set of heap cells, how it is going to be maintained by this deadline IO scheduler, also how it can be exploited. Okay, so I will start with the one operation called insert. So this insert is an operation which take a request and put the request somewhere in the tree. In the first queue, Q1. So what it does first is it first search the linked list and add it to the doubly linked list. So it add it like this. And after that, it search the tree, and then it find the right spot to insert the node. So it goes like this, and then it insert the element. So at the end of the operation, you can actually see that we still have a list and trees overlaid one top of the another, and then these two tree and list data structures are talking about exactly the same set of heap cells. So that kind of correlation property is maintained by this insert operation. A bit more interesting thing is a move request. So now what it does is it search some request which satisfy certain property, and it moves that request from the first queue to the second queue. And these operations actually exploit this correlation property. I will explain it how it works. So first it finds the request. So it traverses doubly linked list and find a node like this one. And then it eliminates the nodes from the doubly linked list. Okay. Yes, it deletes the node from doubly linked list. And then it deletes the node from the tree. But one interesting thing about this deletion of a node from the tree is this deletion happens, in a sense, in place, without really traversing the entire tree. That's possible because we know that once I find the request in a doubly linked list, that node is also in the tree as well because of the correlation property that I just told you. So how the operation works is it traverses its parent pointer and find out which guy is actually pointing to this request in the tree, and it resets its proper child, in this case, right child, into 0, so that's effectively eliminate the node from the doubly link from the tree. So this is a place where actually this property, tree and list, talk about same set of heap cell is exploited. Because if that property is not there, then following this parent pointer, because it's a C, I might end up with a dangling pointer. So if I try to do anything with it, this is not going to be a memory safe operation. So then it adds elements to the nodes like this. So now you can see that, again, at the end of the day, we still maintain the correlation. Just like I told you, this tree deletion operation actually exploits this weak correlation property. So when I and my friend looked at this program, we developed verification algorithm which can actually exploit this correlation property, and so that the analyzer can prove the deadline routines in deadline IO scheduler, but at the same time sufficiently efficient. Okay, but our verification work actually started quite a long time ago. In 2009, I and my friend Rasmus Petersen, we first thought, okay, this is an interesting program, and then we want to develop verifier for those programs. But we didn't fully understand what's going on in the source code, so we developed the code, and we have both precision and performance problem. So we don't track enough correlation, but at the same time, we track unnecessary correlation, so we just end up with something which doesn't really work. And then we realized, actually, we have to throw away lots of correlations. So we have another version which throw away lots of correlation. So it worked almost all the routine except one in the deadline IO scheduler, and that's the place where that weak correlation that I just told you is exploited. So this guy doesn't really prove the entire deadline IO scheduler. Yes?
So just namely, so memory safety means that every pointer that's accessed has been allocated and not free.
Memory safety means no dangling pointer dereference, no null pointer dereference, yes, and also no memory leak. So, but then what we really prove is what we call shape property, which is at each program point, what are the expected data structure invariants, and this verifier shows that these are the expected data structure invariant. So I will show you some demo, and you will see some pictures.
The absence of memory leak is more than safety.
Oh, if
okay. But
yes. So now so then we gave up. Then my friend Oukseh joined this year because he had a sabbatical, and we approached the problem again, and then we were able to actually prove the entire deadline IO schedule. Modular, we do some modeling, so there are some hacks or cheating we have done, but even with that cheating, we couldn't really do it because I thought it's a quite hard problem. So anyhow, that's what I've done, and I will show you the demo about.
What's your, how do you model the operational semantics of the program?
So the operational semantics, you mean operational semantics of C?
Yeah.
Yeah, so we had a particular operational semantics. Actually, you can say our operational semantics is encoded inside the implementations. So then the memory model, we use the memory model inside in CIL. So that's, in a sense, not as precise as in real C semantics, but it was, so what we are aiming for is kind of conditional proof, soundness, conditional correctness. Assuming this memory model it doesn't really generate any new issues, then we have a correctness.
So are you going to talk about what is the memory model?
Not really.
Okay.
Okay.
How big is this IO scheduler?
Okay, I will show you now. So this is IO scheduler. It has bunch of inline code and some my creation routine. So it is, quite, well, this is not very visible, but so this guy is, but it's still reasonably big. It's a 2,000, with declaration, it's about 4,000 lines of code. course, there are lots of comments and so on, but I thought it's realistic. And then this is like main routines. What it does is it creates a data structure. Data structure creation can fail, then it just returns. Otherwise, there's a really big non-deterministic while loop. It keeps exercise all the routines in deadline IO schedule. So deadline IO schedule is like a library. So what it does is generate typical data structure, and big while loop just keep exercising all these library routines. So I commented out the main part because it takes about 400 seconds. So I will just show you the analysis result after the creations, so that you can see how data structure actually look like. So
you do inline procedures?
No, we implemented RHS.
Okay.
Yes. So now analysis is finished. So it generates a bunch of pictures. But, okay. So these are all global variables used inside deadline IO scheduler. And what this picture shows is that this picture shows how our analyzer actually works. Our analysis tool tries to analyze this list part and tree part as separately as possible. So this picture only shows what we're going to get from the list analysis part about the list. So this one, say there are doubly-linked lists which have some header. These are some errors from the drawing tool. And there's another doubly-linked list. So remember the deadline IO scheduler, there are two doubly-linked lists. One is for Q1, the second is for Q2. And these two doubly-linked lists actually mirrors those two data structures which you saw in the slides. Now I have shown another one. So this is about tree. Again, there are lots of global variables. And important thing is here. So there is a tree, which is for the first data structure. And there are some true predicate, which means essentially as far as the second data structure, which is Q2 is concerned, we don't maintain any tree structure. So this true predicate covers the Q2 from the tree's perspective. So this picture actually shows how our analysis tool actually works. It tries to analyze this part and tree part as separately as possible. So the idea is that because these two data structures are weakly correlated, it really encourages us to have very weakly correlated on two analysis tools. But they have to talk to each other a little bit. So that's in the rest of the talks, what I will focus is how that weak correlation actually happens. Before that, I'll just run the tool. So it will take about 400 seconds, and then I will just continue my talk. Hopefully at the end of the talk, it finishes. Okay. So design principle is the idea is that to analyze the tree and list as separately as possible. And what we think is in doing so, we can get some gain in performance, but this separation cannot be done in a complete manner. So they have to talk to one another a little bit. And in terms of techniques, I found quite interesting technique is that we found that if we use ghost variable, and during the analysis we discover instruction on the ghost variable on the fly, then we found that that's one good way to make those two tools to talk to each other. So traditionally, if you are familiar with program analysis, people use so-called reduced products or some other mechanisms which is statically determined. But what we found is that using ghost variable is another good way to make that communication in a very cheap, effective manner. So now I will explain what's going on. And to do that, you need to understand a little bit about separation logic. But it's okay. It's not very hard. You can just understand what separation logic formula means in terms of pictures. The first formula, which say x points to pred y next z, which you see on the top here. This one say, I have a cell X, whose previous field is Y, whose next field is Z, and it might contain some other field. So we don't really care about some other field. So for instance, in this case, it has a field F, we don't really say what the value of f is. The second formula is non-empty. It's a doubly linked list. So you say I have a doubly linked list starting from y, ending with z. So I have a doubly linked list starting from y, ending with z. And the previous value of y is equal to a. So just like you see here. Next value of z is equal to b, just like b you see on the top. And then this any means this is non-empty doubly linked list predicate. And we also introduced some tree segment predicate because this deadline IO scheduler actually uses trees. So this predicate say I have a tree rooted at x, but it's a segment, so there are just some edges which is going out from the tree to the outside. So this y is talking about the pointer from this kind of last cell in the tree from where some pointer goes from the tree to the outside. This b is a target of that pointer. So this is a tree x, but there are some hole called y. From y, there is a pointer to the outside, which is b. And then a is a like parent's value of tree predicate x. Yes?
And you only have a 4-array version of this tree. You don't have exceptions for b and c and d.
No. That's right. So we don't have multiple trees with multiple holes.
Because the programs only violate the invariants in one point at a time.
That's right. Or programs, so like suppose I want to verify, say, breadth for search. This kind of predicate is not good enough. What happens is analyzer will diverge or just start to be stopped by me because this predicate is not good enough to summarize some regularity which is going on in depth first traversal. So this is very targeted for certain kind of tree operations where one hole is good enough.
Right, but it has an obvious generalization, which is sort of any number of fixed.
Yes. So now that that's right. So if we do it, so manual verification is not really a problem, but if I do the automatic verification, that means now I have to design abstract domain for strings. So it's because holes can increase as many times. So that's one direction which we haven't pursued. I thought it's too much. It's already, there are some other works needs to be done. So now, interesting part of separation logic is separating conjunction. Perhaps you heard about separation logic so many times, so you now understand. This separation conjunction said, I can split it into two parts. Left-hand side of one part satisfies the left-hand side of formula. The other part satisfies the right-hand side of the formula. And the picture you see on the bottom actually satisfies the formula on here because I can split it here. Then this cell x satisfies the formula x points to 0y because its previous value is 0, its next value is y. Then the other side satisfies this list segment predicate because I have a double linked list segment from y to z, which is non-empty, and its previous and next fields are set correctly. And separation logic is just normal logic, so it has existential quantification and universal, as well as conjunction and disjunction. Now, one idea we have was to use only special kind of separation logic formula, which is good enough to capture these weak correlation properties that I just told you in deadline IO scheduler. So don't worry about this gamma, beta, alpha at the moment, okay? And this formula, this is the represent kind of typical formula which is used during the analysis. This formula is a conjunction on the top and has a one part for the conjunct, the other part for the conjunct. The second part. The first part talk about tree-related properties only. And the second part talk about list-related properties. Now, if I do it, we cannot express correlation between these tree and list data structures. That's necessary to prove the memory safety of the program.
What is the correlation fact you want to express?
The tree and the first queue, tree and list are talking about exactly the same set of heap cells. So what we did was we actually augmented or extended this separation logic formula with, you can say, second order variables. These second order variables like a gamma, beta, alpha represent settable locations. But then this settable using this, we can say the first guy are talking about exactly the same set of locations. The second guy talk about exactly the same set of locations. The third one is the same. And the formula also have primed variable, which are implicitly existentially quantified. So E prime, I'm not going to write existential quantification, but if you see primed variable, just understand it as existentially quantified variables. Okay? But note that these alpha, beta, gamma are not existentially quantified. They are ghost variable in the program, which will be manipulated by the instructions in the program.
But why are they appearing in the subscript and so on?
Oh, it's just syntax. So we extended the separation logic formula so that every predicate comes with this alpha, beta, gamma. And then what we wanted was this alpha, beta, gamma. We don't have any extra constraint on alpha, beta, gamma. We just use alpha, beta, gamma as a subscript. That's the only uses of alpha, beta, gamma.
So if you took them away, it would still work?
If we took them away, if I run the analysis doesn't keep track enough information so that we cannot really prove memory safety of the particular routine, which is move routine.
So alpha, beta, and gamma are program variables, right? You are going to add some ghost variables,
yes.
And you're going to update them as you go along in the program.
That's right. That's right.
And now this formula is referring to those ghost variables also.
That's right. That's right.
Okay.
And then alpha, beta, gammas are the kind of instructions which manipulate alpha, beta, gamma are going to be inserted by the analyzer.
Right.
So then that's a way to make tree analyzer.
Can I think of beta as sort of representing a set of objects?
Yes, set of addresses.
Set of objects.
Yes, set of addresses.
And so you keep adding and removing stuff from them.
Yes.
Okay.
So then this set of addresses means everything, all the heap cell involved in this tree is exactly same as the sets. If I collect them and make a set, that's same as this set beta.
This means you have 3 heaps essentially, alpha, beta, gamma.
Yes. That's right. So now I'll show you the example, and it will become a bit clear. This first part talk about only tree. So now you see that there are trees, like cell Q1, also tree. And if I erase all the link, what you see on the right-hand side is just a bunch of cells which is summarized by true predicates. The second one is a list, and it just describe how it looks like if you focus on the list, the list part only. Okay, now using this alpha, beta, gamma, we can now talk about the correlation between these two conjunct. Yes?
Is there an intuition here? If you have a data structure, you have the beginning, the data structure, the body, and the ends. Where the alpha, beta, gamma coming from?
So alpha, beta, gamma is, in a sense, you're right. Alpha, beta, gamma is mainly, the intuition is that we design analyzer so that alpha, beta, gamma captures the group of data structure. Like alpha is for captures all the data structure involved in one object, in some one high-level object like a trees and list. So during the analysis, this predicate can be decomposed into multiple components, but still we want to use if nothing really changes, then we want to put group all these things into some one same second-order variable like beta. So it provides one more hierarchy which say which kind of heap cells should be considered as a single unit. Okay. So then beta is for the trees and lists, and gamma is for the linked list, what you see on the right-hand side. Okay. So now, as I said, this expressed the loose correlations. Now because, reordering this doubly linked list still satisfies the data structure. So what it really captures is this formula captures the lists and trees are talking about exactly the same set of heap cells. So, but on the other hand, if I add some nodes like tree, but without updating this link field, it doesn't satisfy it because the beta predicates say this tree and list should talk about exactly the same set of heap cells. Yes?
I want to follow up on that question about these representing distinct subheaps. So the formula that you've got written there has the separated conjunction on the inside and the regular conjunction on the outside.
Yes.
If you did it the other way around.
That's in some sense what you're saying is exactly right. Original motivation was suppose we nest separating conjunction and normal conjunction in arbitrary manner, then many of these properties can be expressed. So you especially say exactly as you said, put a conjunction here and using separating conjunction outside, that can be used to express it. But now the problem becomes, how can we design the rest of the analysis, which is transfer functions and abstraction mechanisms or join operations. So it was if we have an arbitrary complicated formula, we gain something on the expressiveness, but on the other hand, we pay the price about designing the right the abstract transfer functions. So this particular representation is designed so that many of the existing transfer functions can be reused without changing very much. Okay? So right, the abstract domain is really a disjunction of these guys. So we have disjunction of a tree predicate and conjunction outside and disjunction of another list predicate. So in a sense, what we are doing is a Cartesian products of two abstract domain or two power set abstract domain. The first power set talk about tree-related property using disjunctions. Second power set talk about list-related property using another disjunctions. And these two power sets, they talk to each other used via this ghost variable beta, gamma, and alpha. Okay, so that was the kind of basic form of the analysis. Okay, we set up abstract domain in this way. Now the main question becomes, if you just run analyzer 1 and list and tree separately, then there's nothing to say about this talk, but it's not good enough. So we have to make these two components to talk to each other without paying too much price. So I will show you how actually that works by going through this particular routine, which is a move routine. And ideally, we like to have a list analysis in the one go and tree analysis in another go. But the problem is when you do the tree analysis at this point, we have no idea, we have no information about where RQ is. So we cannot really prove the memory safety. So what we do is our analyzer goes through two phases. The first phase is it runs some form of pre-analysis. You can say, you can understand it as a meta-analysis, which try to figure out what's going to happen when I run tree analyzer and list analyzer separately. And then that meta-analysis say, oh, actually, this tree analyzer and list analyzer has to talk to each other at certain points. And it inserts ghost instructions. We say, okay, at this point, these two guys have to communicate. At this point, we have to maintain this ghost variable in a certain way. And then it runs, after this insertion of some of the ghost instruction via pre-analysis, it runs the main analysis. And the main analysis itself can also add another instructions. So in this case, if I run this analysis with the predicate that I showed you in the previous slides, the analyzer also inserts instruction of this form, which is saying we have to unify certain ghost variables. So it is like we try to put these ghost variables, instructions about ghost variable as much, to the pre-analysis as much as possible, because that makes our analyzer more predictable. But there are some cases where it's not possible. So, and this unification is actually happens, because that's where to insert unification can be only available. That information is only available during the real analysis. Okay?
That's a union or unification?
So it's semantically take all the variable gamma and all the variable delta, and then take a union of them and then put it to gamma and set delta to 0. But yeah, it's a set union and set delta to 0. I didn't delta to the empty set. So then one way to implement that is via unification. Okay, and these are the instructions which is added, and they are the one which make these two analyzers to talk to each other.
So how do you implement those?
Oh, I will tell you later. Okay, so suppose it was added. So the last one, I will show you how it works. But the other two, I will tell you later. And suppose it works, then let's see how the analyzer actually make two lists and tree analysis to talk to one another. So now this is the same move routine. And it first finds some requests from the Q1. So like this. And then it deletes the request from the doubly-linked list. So now, think about I will show you what's going to happen after this. What analyzer will produce after the first two instructions. Analyzer will replace the list, this second star conjunct in the list part by what you see on the bottom. What it says is, I have a list, Q1. Then this guy say, I have a doubly linked list segment from C prime, D prime, and then its previous and next, all of them points to Q1. So these two star conjuncts describe the doubly linked list, which you see on the three, consisting of the three nodes. And then the points predicate on the right-hand side express the request, the request node, which is taken out from the doubly linked list. Okay. Now, the next instruction is move informations. What it says is that move information from the second list part of the analysis to the first, which is a tree part of the analysis. And especially, we only move the information with respect to this RQ. And this, so what it does is, analyzer first figures out RQ is in the region beta because it's annotated with beta. So which means the set value of beta contains RQ. And it moves that information to the tree part. So it say that, okay, RQ should be somewhere in the beta partitions. So then we can replace this tree predicate by, somehow instantiate that tree predicate such that this RQ fact is explicit inside the predicate. So this, I didn't really show everything, but it say that I have a tree which is kind of everything which reaches RQ nodes. And then we have RQ node explicitly. And then there are something which comes below the RQ node. So if you see I have a tree, RQ is somewhere. There's something which is before the RQ. There's something after the RQ. And this predicate describes that fact exactly.
So is that beta a upper bound on the set of elements?
So that's, very good point. I think beta should, when you define the star, the notion of a star should also split the definition of beta. So beta, notion of a star, say I can split it into two parts. In the same way, beta should split this definition of beta into two disjoint subsets, so that beta here and beta here talk about disjoint sets of locations. So it's a little bit more sophisticated, but I just didn't quite explain everything. So now if I delete tree, then this node is gone from the tree, and that operation can be run symbolically with respect to this, the description of our tree that we have. So that will replace.
What you just explained is not the semantics of separation logic, right?
That's right. It's different. So, but semantics of separation logic, what I think is, separation logic is essentially whenever you have a partial commutative monoid, you can always define the notion of a star based on partial commutative monoid. What I'm exploiting here is that I just extended existing partial commutative monoid with something extra, which is the value of beta and alpha and gamma. And then now, once I have this PCM structure, I can always extend the logical formula for those predicates. So in some sense,
so what you're saying is that there is no one separation logic.
Exactly, yes. So I think separation logic, personally, my take about separation logic is not like a first order logic. It's more about semantic principle, which can be exploited in a certain way. So whenever there is a notion of a separation expressed by the partial commutative monoid structure, then I can always come up with a separation logic very easily.
So in other words, the syntax used to express formulas is not that big a deal.
That's right.
Really the essence, the way you derive all your intuition is based on the models.
That's right, exactly. So, and the syntax is kind of semi-automatic. Once you have it, then there are kind of good recipe to produce syntax.
And then how do you reason about these formulas?
So then these are all instances of something called the logical bunched implications. So and then that proof rules carry over, so I can just reuse those proof rules.
So whenever the semantic models are based on these partially commutative monoids, the proof rules of this logic of bunch implications will do the job?
Yes. So that's not good, it's not complete, but it gives just basic implications. Then for specific cases, we have to come up with the other implication fact. But my experience is because these formulas are so simple and the variant is very little, the kind of implication we have to consider is not very much. So for particular implementation we are working on right now, we don't really do anything special for this beta. Most of the existing theorem proving questions, theorem prover, or theorem proving techniques can be carried over in these extensions. And then we don't do anything special for alpha and beta. Okay, so move on. Then now, the next one is what we call transfer, which is now what it does is it transfers this cell RQ from partition beta to partition delta. And that is, the reason it does it is if you understand what's going to happen in the future is that you can somehow see why we do this, because we want to move this RQ from partition B, this tree, to the list. So we do ownership transfer of this cell RQ from the tree to the list. So this intermediate step, reassigning delta to moving this RQ from beta to delta serves as a kind of preparation step for this ownership transfer. So initially we have beta, and then we split beta into like this, and then we just name this RQ as a delta. So now at the end we have this list insert operations. So this list insert operations works like this. So it adds this node RQ to the second linked list Q2. And symbolically, what it does is that after that list insert operation, we have this representation which say, if I have a double linked list starting from RQ2 and go to E prime, and then it points to RQ. From RQ, it points to Q2 again. So I have a cyclic double linked list. So it's a symbolic way to represent what's going to happen in the actual operation. Right. So now, when the analyzer sees of this form, it figures out actually I can abstract this. This is essentially cyclic linked list. I can express this cyclic linked list with one predicate, which is lists any predicates. But then we realize that actually we cannot do it because there are these partition delta and partition gamma are different. Or you can of course do it, but if I do it, I have to make sure that all these tree and list analyzers have the consistent view about this gamma and delta. So what it do is it's first merge, kind of unify this delta region and gamma region. So like this. So then at the end of this unifications or kind of merge, we have one region called gamma, which includes the both requests and this list segment predicates. And then there we can apply the abstractions. Then abstraction make summarize the entire predicate as a single list segment predicate. Now one effect of this is, now this instruction will be also run for the tree part. So then this will replace the text from delta to gamma, and it's going to be merged with the true. So that's the result at the end, what we get from the analysis of this routine. So this is the result we get at the end of the analysis. We say that we have a tree, Q1, which is a tree, and we also have a Q1 and Q2, and then this Q1, the tree and list are talking about exactly the same set of heap sets. Yes?
So I have a high-level, meta-level question about your approach.
Yes.
So when you set out trying to do this verification, you spend some time designing the logic itself, right?
Yes, yes.
And then you spend some more time designing the abstract interpretation business, right? The transfer functions and the join and widen and all that stuff, right?
Yes, yes.
Now, how much would you say, how much time did you spend in the first part, how much time did you spend in the second part?
So actually the real story is, at the moment, for this particular project, we think about problem and then we do so after having some agreement about, the real story is spend most of the time in the implementations. So designing, once we fix the abstract domain, like the one that I showed in the first few slides, then the other operations the other operations are just, we can think about it and then see how it should be implemented. So the story is, we have said, okay, we need these much operations, and then we just implemented them first, and then the theory just came up later. So I know this is not a good answer, but I cannot really measure how much I really spent. For designing this abstract domain, kind of logic itself was really easy. So that part was not really a big deal. It's more like designing some algorithm for abstract interpretation. And
so then what I don't understand is that supposing you designed the logic, right? This program is what? Maybe a few thousand lines, right?
Yes.
Not a super large program. You could have then decided to write all the loop invariants. You have a theorem prover. You have an incomplete theorem prover for these kinds of formulas based on the proof rules for logical function implication, right?
So then, I actually did hand proof before, during my PhD. If you ask me, do you want to do hand proof or do you want to do design such an analyzer? I prefer the second option because hand proof is still extremely painful. So
but it's not a hand proof, right? Because you only supply the loop invariants. Everything else will be taken care of by the prover, right?
No, there are many of the procedures.
Huh?
During the PhD, the prover did not exist. Now it exists.
Yes, but then also it's a bit more complicated than that because now I have to give pre and post conditions for each procedures, and then there is giving a pre-post condition for procedure involves so-called cut point. So Noam-Rinetsky called cut point, which means you actually have to add logical variables. If you don't add logical variables, you cannot really relate certain relationship and pre and post. And I identify how many logical variables I should add is much more complicated. So personally, if somebody say my boss asked me to do manual proof with the infrastructure I have, and if we give yet another option, say, okay, develop a verifier, I think developing verifier for me, it's a lot easier to do that.
So, but still, I don't understand. No matter what you do, at the end of the day, even if you use program analysis or abstract interpretation, it is computing at the end of the day and inductive proof, right?
Mm-hmm.
So, how do you check? There must be some step that checks that proof is valid, right?
Yes.
Who is doing that checking?
So, the abstract interpreters use sound implication, right? So whenever you do the over approximations, it always produce, suppose all the steps of abstract interpreters are correct, then it will always produce an over approximation of each step. All you need to check is syntactically I reached the fixed point or not. So abstract interpreter, in a sense, put a less burden to the theorem prover because many of the good reasoning is incorporated into the development of these transfer functions, and many check about whether I reach the fixed point can be actually reduced to syntactic checking. Okay, so personally, but developing these tools, I personally find that interacting with some kind of this one, instead of providing the actual proof or loop invariant, providing some of these hints or helping a little bit, that is much more enjoyable and much easier to do that. Okay, but just my personal opinion. And another thing is there are some other class of program which I believe follow the same patterns. Then the technology can be applied there. Right. So now I sum up some abstract operators. The abstract domain is, you can say, power set domain of tree and list. And then these domains have three operations, which is move information from tree to the list to the tree with respect to cell X, or transfer the partition of cell X to the partition alpha. Also, we have some union operation or some, you can say, unification operations. And these three operations are used to make these analyses to talk to one another. Now, and then I just want to point out one thing. Then this operation, which you see on the bottom, is mainly discovered based on where we should apply abstractions. So abstraction is summarizing data structure into a single list segment predicate. That was a driving force to, for the inferring where we should put the third instruction. But the other two, actually we use pre-analysis to figure out where we should insert the other two. And I will show you how it works there. Okay, so to figure out the other two, we, in a sense, do meta-analysis. We do analysis which try to figure out, it's formulated in terms of data flow analysis, but that analysis try to figure out, okay, if I run tree analysis, what's going to happen? So for transfer functions, what we do is that if the meta-analysis figures out, if we run tree analysis and list analysis, then we know that this RQ will be expressed as a points to fact. I mean, as a point, not inside the inductive definitions, but as a points to predicate explicitly. And that's the point where we insert RQ, these transfer instructions, which means whenever we see this RQ as a points to blah, so not inside the inductive definitions, then we temporarily put it into the region delta that might go back to the original partitions or move to the next partitions. So this is what's be done by the analyzer. And the second one is now where we should insert this move info instruction. Now, to find it out, we do forward analysis and backward analysis. The forward analysis figures out that whether tree knows about RQ or list knows about RQ. So then this forward analysis figures out that at this program point, it's likely that tree and analyzer that will know about where RQ is actually allocated. But it's like, I mean, then this analysis cannot really conclude, no, list analyzer knows about where RQ is allocated, but it doesn't really know tree will know about RQ or not. On the other hand, its backward analysis say that at this point, to proceed, this tree part actually has to know about this RQ. So we do this forward analysis to figure out which part of the analysis knows about this cell RQ, and then which part of the analysis which needs information about the RQ, and then that's the point where we actually insert this move info information, move info instruction. And for this deadline IO scheduler, this is formulated using some data flow fixed point style meta-analysis, and it inserts about 4 or 5 instructions, these move info instructions, into the program. Okay, so this is the end of my talk, and yes?
I have one more question.
Yes.
Again, a meta-level question. When you design the abstract domain for a program,
Yes.
in that process, do you feel like you got some more insight into why the program is correct?
Yes, that's actually true, yes. So for this deadline IO scheduler, I didn't really know that weak correlation before. So this...
Well, I see. But I thought that the weak correlation, that insight came when you were trying to design the logic, not when you were trying to design the abstract domain and the transfer function and so on.
So I cannot really...
make a distinction between
That's
the
right.
two
I don't
phases.
really make the distinction because for me, designing a logic is so easy. So I mean, because it's not, so designing logic really means coming up with partial commutative monoid. So once identifying which partial commutative monoid is necessary is closely tied to how analyzer is going to work. So like all the rest syntax is, because I'm so used to it, just follow very automatically. So the first take-home message is there are many of these overlay data structure, and I expect many, maybe not all of them, but quite few of them uses this correlation only. So when you kind of face exactly same problem, think about just whether this guy have only this weak correlation or not, and if you are happy with using separation logic, try to use these conjunctions and star and second order variable. The second take-home message is the following, which I quite liked it because, suppose you have, your boss asks you to combine very expensive analysis. Disjunctive analysis are very expensive. Want to put 2 disjunctive analysis together. That's actually what we are doing. This one disjunctive analysis for tree, another disjunctive analysis for list. If you expand, if you implement that so-called reduction operator, which is by expanding all these conjuncts. So if I have 5 disjuncts, 10 disjuncts, have a conjunction of them, you can generate 50 cases, right? If you do those 50 cases and do some operations on them, very likely it's going to perform very, very poorly because it goes exponential, not exponential, but I found it quite challenging. On the other hand, another strategy is kind of treat this case splitting in an implicit manner. One way to do it is using ghost variable, adding ghost variable, and make analysis to insert these ghost instructions so that these 2 analyzers have a consistent view about ghost variable. Okay, so that's the end of my talk, and I will just go back to the tool and say, okay, it's verified, and nothing fantastic. Oh, nothing like fancy, but the tool was able to verify that code is okay. Okay, thank you very much.
So, can you rephrase the use of ghost variables and the transfer functions as a reduced product?
Yes, so but usually reduced product is explained in terms of this. Once I fix state space, meaning once I fix the set of variables, then that's usually a way to explain reduced product. But it's a bit, I mean, if I exaggerate a little bit, it's a bit like once you have existential quantifications, your conjunction, I mean, you can exploit that existential quantification to talk about a lot more. So if you are allowed to expand the state space, so I think.
So are there? So you have rules. So there's a principle.
Yes.
That you could specify or formulate based on.
Yes.
Although your presentation implied that you use that you insert functions, the transfer functions by pre-analysis phase.
So yeah, right. But then also on the fly, if it's necessary, we can insert these ghost instructions. So the whole the kind of principle is that now I want to put two analyses together. One possibility is extend the state space by adding some ghost variables. And then during the analysis, figures out how to update this ghost variable. And that inserted ghost assignment will play the role of communications between these two analyzers.
Does this pre-analysis, does it know what tree deletion is, or does it somehow, look first at the tree deletion, figures out what it does, and then? So
the pre-analysis mostly try to guess things in terms of reachability. So it's a heuristic, but instead of a tree, it say, okay, if I have some root x, I want to know all the things reachable from x via this field of the tree. So the whole analyzer which I described is parameterized a set of fields. So I just initial configuration file say, okay, these fields should consider as one conjunct. These set of fields will be tracked by another conjunct. Then based on that set of fields, it uses kind of reachability style reasoning to figure out which, what we call view really knows about what's going on there. So not tied to the trees. Yes?
It's kind of, I guess, maybe anybody might feel free to answer this because I have little experience in that area, but if you were to pose this problem to me, my first reaction would have been to actually do a dynamic analysis where I start kind of exploring, like I just start creating models, like essentially fuzzing the data structure. Because I'm just looking over, it seems like I have a small state space to search before I could keep looking for new shapes, but I would expect this small program.
The answer to your question is that here the approach is non-negotiable. We have decided on what the approach is. Can't change it.
Well, I think it's great that we're exploring the extents of this approach and making new bounds, but I'm just kind of curious.
One possibility, I think like dynamic analysis can play a big role in shape analysis as well. So suppose, how can we figure out what data structures are actually used? And then suppose I have, C for this kind of code, I don't have a good dynamic profiler. But if suppose I have a good dynamic profiler, then I can gather some of the heap shapes. They give us, certain abstraction may be applicable here. Certain abstraction is not applicable because applying abstraction at the end, I just got exactly the same heap. Then this is useless. So actually, Muli and Mayur, they do similar case study for Java. So what they did was for certain kind of particular applications, they tested whether, they collect the heap from dynamic analysis and apply the abstractions, whether they check whether certain abstraction is good for that or not. So I'm sure there are lots of rooms for dynamic analysis. Just I don't really know what to do at the moment.
So I guess what I was really looking for is this is for a 4,000 line program. I was hoping you'd say something along the lines of, okay, now we start doing this from the Windows kernel, which is not 4,000 lines, and now this dynamic analysis will get lost, while the static analysis might be composable or something like that.
But another possibility, I prepared it so that now I have a main routine, so then I can just run this main entire code and collect some data. So it's not fully dynamic. So I already prepared, because this is a library, I prepared the mains. I run the routine, then I get some features about, okay, what kind of correlation is important and so on. Then that could be used. But it's a kind of direction which I haven't explored.
So this one takes almost a gigabyte?
Yeah, yes.
So the invariance that the abstract interpreter is computing is very, very large.
Yes. So some cases, the preconditions, yes, about 3,000 preconditions. So there are rotate routines, and then the preconditions are 3,000. I mean, of course, that's because the analyzer makes some rough guess. And I can actually show some statistics here.
This is pretty amazing.
So did you prove that just the driver of this that particular while loop at the end is safe, or that is this package that has like this entire library is safe?
Yes, it's I mean, I'm sorry, what did you ask?
So at the end of your C program, you uncommented this while loop that emphasized your code, and you're verifying that this while loop is safe.
Yes, but then from that while loop we can reach everywhere. I mean, I think it reaches almost everywhere in the source code. Because these are like a library, so usually it has an export some method, and it just exercises all these methods. And
we don't have specifications in the
well, he has this property that this property is maintained at every step of line of code, and so it can reach every step.
But at this program point, I mean, the invariant are complete is not necessarily what you see on the slide. It could be anything, but so see that. Some routine has, 100 preconditions. Some like red-black tree inserts has 150. Well, not really. So, okay. I think this is not very useful. Yeah, some cases it has about 400 preconditions and so on. So it's just doing it by hand could be quite challenging. I mean, of course, human can optimize, but it'd be still quite challenging. And I think actually analyzing trees is much more difficult than analyzing linked lists. So look at perhaps maybe it's the same in Windows, but Linux trees are much more challenging. Okay, thank you very much. Yes.